Welcome to our project on computer vision technology for visually impaired assistants. So visual impairment poses significant challenges in daily lives, making tasks like navigating environments and identifying objects difficult. So we need an assistive technology to empower visually impaired individuals. So our solution is to develop a computer vision system that utilizes deep learning and stereo vision to provide real-time assistance. It detects and localizes objects, providing auditory feedback about their presence and location. So our goal is to create a portable, user-friendly device that enhances spatial awareness and quality of life for visually impaired individuals. Join us as we explore the technical aspects and potential impact of our project.
So now we're going to move on to the stereo vision component of it. So we implemented a stereo vision model trying to emulate human binocular vision using two webcams set up directly next to each other. So the only difference in position between the two was the horizontal translation between the two. And both of these webcams were ordered at the same time. They're the same camera, nearly identical, but we'll discuss more of their differences in our challenges section. From there, we calibrated the two cameras to understand their intrinsic properties. So first we utilized a chessboard image, which we kind of waved around the two cameras at multiple different angles. From there, we were, because of the chessboard image, it's really easy to pick out corners, and there's a find chessboard corners tool in OpenCV, so that helped out a lot. From there, we were able to pick out all the matching features between the two cameras and then match those accordingly. From there, all the corresponding 3D points, which are calculated using the width of each square in the chessboard, as well as the image 2D points, which were taken using the find chessboard corners function. Those were used to map the world to camera transformation and then the projection transformation, which was used to compute the camera's intrinsic and distortion matrices, as well as our depth stereo maps. From there, we were able to perform depth estimation. So our approach was using Yolo boxes. So Yolo boxes were the tool that we used to compute, to detect objects and determine what kind of object there were. So as you can see in the image, we were able to find a person, and the view of the person is slightly different between the two cameras. We computed the center of the Yolo box. They were pretty tight, so it's a good measure of where the object is in both images. And using that disparity, we were able to calculate the depth.
Another thing we tried doing was to experiment with different Yolo models, such as the Yolo V8 Ultralytics model shown here. One advantage of this model is that it was pretty responsively good at identifying objects in real time, and it was even robust at continuing to identify an object when you move towards it, as you can see with this chair. However, one downside with this model is that even though it ran pretty well on my PC, we were ultimately unable to replicate that on the laptop, which is why we chose to go with the darknet model instead.
Audio feedback for the user is an essential function of our project. We decided to use 3 tones, the lowest representing an object 6 feet or further away from the user, the middle frequency used for a distance between 3 feet and 6 feet, and the highest frequency for objects closer than 3 feet. Originally, we were going to use volume to differentiate object distances, but we thought that having different tones would be more distinguishable. We also implemented spatialization, where an object on the left side of the view field will alert the user only using the left speaker channel, and the same for the right side. If the object is in the middle third of the screen, then the tone will play from both speakers.
Check out a live demo of our project with our screen being recorded showing you what the computer sees. On a final note, we did encounter a few difficulties, the first one being image rectification difficulties due to high distortion in the right camera, the second one being limited resources for fast object detection computations, and our third being scarcity of readily available stereo audio libraries. Thank you very much for watching our presentation, and we hope you enjoyed it.